Hello, everyone. Thank you for attending this session. Today, I'll be presenting embedded pore solution resistivity sensor for concrete materials. I do want to acknowledge and thank my advisor, Dr. Farshad, and the persons who were involved in this project, Dr. Shiro and Dr. Kopa. And this project is a collaboration between Penn State University and Calentis Consulting Group. So also, I do want to thank their involvement, Dr. Nima and Dr. Kostia, for their work as well in this project. So I will start by project review, then discussion for literature review and the objectives, and then I'll be covering methodology, results, application, and finally conclusion. So why do we measure pore solution resistivity? Well, measuring formation factor as outlined by AASHTO R101 is essential to ensure the adequate durability of concrete. And formation factor is defined as the ratio between mixture resistivity to pore solution resistivity. And while there are lots of standards that discuss how to calculate mixture resistivity, there is no standard on how to calculate the pore solution resistivity. So we're working on creating a sensor that is capable on measuring the pore solution resistivity to fulfill this cause. So what are the applications? Well, as we said, adequate and accurate estimation of pore solution will help us in accurately measuring the formation factor. And formation factor correlates with lots of important characteristics in concrete. Halzel's study showed that formation factor highly correlate with the chloride migration coefficient and water absorption, showing a coefficient of determination higher than 93% and 91% respectively. And in another study by Dr. Weiss, it was shown that formation factor can be very helpful in predicting the corrosion onset in reinforced concrete with varying covers. So we talked a lot about the pore solution. So how do we estimate the pore solution resistivity? There are three main common methods to determine the pore solution. First, through extraction, where we crush the concrete into small particles, and then we pressure it at 1,000 MPa in order to squeeze the liquid, and then we measure the resistivity through a resistivity cell. And this method is very helpful. However, it's very energy intensive and requires time-consuming as well, and involve large operation requirements. The second method is through NIST model. So what NIST model does is it estimates the ionic concentration of pore solution based on assumption for the ingredients reactivity between the ingredients of concrete, and based on assumption for the degree of hydration. And then after estimating these concentration, it uses neither equation in order to determine the conductivity of the solution and the pore solution resistivity. However, this method was found inaccurate when SCMs are involved, such as fly ash, and this is due to the difficulty in estimating these ionic concentration within the solution. And the last method is through the bucket test. So we just drop the concrete in a well-known ionic solution, and then the ionic exchange and leaching will occur until we reach an equilibrium where inside the concrete the ions are the same as the solution. So this has the highest error in general, because the equilibrium happens with time, and it depends on the diffusion and the porosity of the sample itself. So in 2006, my advisor, Dr. Farshad, demonstrated that porous material like ceramics or even cement matrix can be used in order to determine the pore solution resistivity. The concept came from calculating formation factor of the sensor itself. So in order to do that, we just multiply the reading from the sensor by a geometrical factor, which is based on the area and length between the terminals. And then this works as similar to mixture resistivity, and then we divide it by the soaking solution resistivity. So in order to calculate the soaking solution, all what we do is we drop the sensor as well in simulated pore solution, and we vacuum saturate the solution until we know that the ions inside the sensor and inside the solutions are matching. So this way, we were able to calculate the formation factor. And by tweaking the equation, whenever I want to predict the pore solution resistivity through the sensor, I only have to multiply the sensor reading, the resistance, by a constant factor which we call the translation factor. So this needs lots of monitoring, so it is very sensitive measurement, and it is affected by the environmental conditions and the moisture content. So we had to do lots of testing to prove this. So how, I keep saying sensor and sensor, so what's our sensor? So it's mainly a metakaolin-based geopolymer, and then we try to make a robust system that is, part of it is the wiring and the size of the sensor, as well as integrity of the structure to prove a reliable measurement of the electrical resistivity. And we had to rely on some porosity properties. So in terms of permeable pores, we needed permeable pores higher than 50% to ensure fast diffusibility. In addition, in order to optimize the sensor size. And the second condition is to have small pore sizes. So the smaller the pore sizes, the more the less the drying, and we want to reach a phase where the sensor does not dry at all. So in order to do so, we relied on the Kelvin equation. So through Kelvin equation, the pore sizes that are less than 20 nanometer is associated with no drying when the relative humidity is higher than 90%. And for this reason, we maximized the pores that have diameter less than 20 nanometer, and we were able to achieve 96%. And as we work to ensure reliable readings, we faced many challenges, and we overcame them. So we had to ensure the stability of the matrix microstructure in order to have reliable measurement on long term. As a second step, we did as well prevent the current leakage, as well as the deterioration of the wire and the electronic sensor. And we did this because in concrete it is high alkalinity medium. So we know that the high alkalinity would deteriorate and even corrode the wires by itself. And lastly, so we did as well calibration for the sensor. So in order to have like calibrated sensor, we need to make sure that we correctly calculated the translation factor. We selected an optimum testing frequency, and we had proper saturation solution. And then we, for the temperature fluctuation, we created our own model that correct the temperature fluctuation. And in order to ensure that the sensors remain saturated while shipping, we had to do our system as well. So we have the sensor preserved and functional upon arrival to client. So what are the things that usually you need to record when you're using the sensor? You only have to measure the resistance of the sensor, record as well the temperature of the sensor, and then the age of the sample while you're doing the testing. And then you multiply by the translation factor, and then you use the temperature correction model, and you will able to have the pore solution resistivity at a specific age at a temperature of 23 at a constant temperature. But prior embedding the sensor in concrete, we need to make sure that the sensor works accurately in simulated solutions. So we did this test where we started saturating in a solution, and we will see that the resistance will drop because the liquid will be saturating and filling the voids. And then after reaching the equilibrium, we tried on another solution with higher molarity, and we repeated the same. So we can see that the shape is an exponential. It takes a couple of days until reaching the resistivity required. And afterwards, we had to make sure that it's also reversible. So we saturate in 0.6 solution to see whether the sensor will be capable of reading the same resistivity as before. And now my colleague will be showing you the sensor and the setup that we have created. So the sensors are carefully packed, and you receive the sensor in a sealed condition. And then when you receive that, you just need to plug it and then put it in a white frame. And then this white frame, we put it in two black stands. I think I have the laser over here. Okay, so the sensor will be used to measure the pore solution resistivity. while the black frame will be used for measuring the mixture resistivity. We'll be able to directly conduct the formation factor from that. And you will need a resipod to determine the mixture resistivity, and any LCR meter will be used to estimate the pore solution resistivity. So now we're ready to evaluate the sensor. So what are the criteria for evaluating the performance of the sensor in concrete? Well, first is precision, or we can call it repeatability as well. We want to make sure that the sensor is reading similarly with the same concrete samples, that they are made from the same batch. So 3 sensors were kept from the same batch and tested for precision. And then we tested 3 different batches from the same mix to make sure that even if we made different batches, we're still getting the same pore solution resistivity. And as for the accuracy, what we did is, so we want to compare the sensor measurement to like a reference method, and we selected the pore solution extraction since it's more accurate. So we'll be crushing, we did crush concrete and measure the solution resistivity and compare it to our sensor measurement. And we had to test different curing methodologies, so we specified lime curing, sealed, and simulated solution. And lastly, we tested different water cement ratio and the involvement of SCMs. And this part is still ongoing, but I'll try to explain some of the results. So first of all, I do want to say our sensor have very high repeatability in measuring concrete pore solution. So when we embedded 3 sensors in batch 1, and then other 3 sensors in a second batch and a third batch, and we calculated as well repeatability for the mixture in itself. The reported measurement at 14 days, 28 days, and 56 days had very high repeatability, so we were able to achieve higher than 92% for all batches, which is a success for the sensor. And for the electrical resistivity, as we said, we will be comparing our sensors to reference, which is from the pore solution extraction. So this graph represents the pore solution resistivity from extraction versus time for 3 different curing methodology. And I do want to say that for the samples that they were in sealed condition and the one that they were cured in simulated solution, they were in similar ranges. However, for the one that was in lime cured condition, we can see that there is jump in resistivity. And this jump is due to the ionic exchange that happens and the leaching with the solution, which will eventually affect the pore solution inside the concrete. So if I want to take a measurement, comparison for the measurements of resistivity at 28 days for the different curing methodology, I can see that for the samples that they were cured in simulated solution, the increase was only 17%. But for the samples that they were in lime water, it did increase to 200%. The measurement doubled nearly the resistivity measurement. So considering the curing is very essential when we deal with the sensor, and now I will present the accuracy of the sensor by comparing it to this result. So the pore solution resistivity of the sensor that they were cured in simulated solution is compared to 2 reference points. So this graph will represent the accuracy of the sensor versus 2 reference extraction points, one from sealed condition and one from simulated solution. If we looked at the sealed condition, we can see that at 7, 14, 28 days, the accuracy was very high. It reached 95% at 28 days, and then it dropped at 56 days. And this is due to the fact that the ionic exchange between the curing solution and the concrete hasn't reached the center of the concrete or the sensor location. And for this reason, the sensor is mirroring the condition where the extraction is from sealed condition. Sorry. However, when we look at the graph where both curing were similar, so we had simulated pore solution. So the curing solution, the simulated solution, was affecting the pore solution extraction since it is for the entire of the concrete. However, it wasn't reaching the sensor yet, so we had a low accuracy compared to 56 days. However, at 56 days, the ionic exchange reached the sensor, and then we can see that the accuracy increased to 92%. So we were able to achieve high accuracy. However, it is limited to the condition of the curing. And this is the ongoing work when we're studying the effect of fly ash in reading the pore solution resistivity. So in terms of repeatability and precision, when we embedded the sensor in concrete with fly ash, we've seen that these concrete were cured in different conditions. We've seen that the precision was still higher than 90%. However, when it comes to the accuracy, if I want to compare the results that we had, which was at 28 days. So we had, with sealed condition, it was the highest, it was 95%. However, when fly ash was included, the accuracy decreased to 84%. And then, as a reference, when we compared the result with the extraction from concrete cured and simulated pore solution, we've seen that at 28 days, the accuracy was 86, and then it increased with time. So the accuracy decreased. However, we are expecting that at 56 days, when we test the results, the accuracy would also increase for the samples with fly ash. So in summary, our sensor was capable of having high repeatability in different curing methodology. And in terms of the composition of pore solution inside the concrete, so the sensor is reading like next to the center of the concrete, while the extraction will give us the entire concrete, which caused like difference, or we had to wait for the fusion weight in order to get like a reliable results and high accuracy. And the highest accuracy recorded was with sealed condition at 28 days with accuracy of 95, and at 56 days with when the curing was simulated pore solution with an accuracy of 92. And we're still doing ongoing testing for the different mix designs. And if you need any more information about the project, please contact me on my email or Nima on his email from Calantis, or visit the website for more information about the sensor. Thank you so much.